Greetings, Jay here, or you may know me as the Astro 30 here yet again, and welcome back to AEL. Now, if you're new to this channel, please consider going down below and subscribing if you haven't done so already. Cheers, guys. This is going to be a longish video, so get your popcorn ready and a beverage of your choice. Now, as you can see, I'm at it again. I've got a PCB routed now for the Elektor Austereo, and it's a 5 watt plus 5 watt stereo amplifier based on the original July-August 1975 article, Project 44 and 46 respectively. So currently at the recording of this part of the video, the PCB is in pre-production and isn't actually here yet, but in this video I will be showing the physical PCB. So this is a 3D render output of the routed PCB, and as we can see here, we've got the power amplifiers up the top, and I basically took the original test PCB that I had routed for the power amp and just imported it into this project. So next to it we've got the power supply, and you'll notice that I've got white lines on the PCB denoting each section of the PCB. So we've got the power supply and regulation circuitry up here, and I will show the schematic in just a moment so we can get some clarity on how everything is wired. Down here is the discrete preamplifier, which I described in another video, and this is a single-sided PCB, so there is going to be a few link wires. There's 12 of them in total. Again, I said in the previous video on this, when I was going to route the PCB, it was going to be single-sided, mainly because it makes it easier to repair if you have to remove components or to make any general modifications to the circuit. So it features board-mounted potentiometers. I mean, you could, if you wanted to, take these off the board and run wires to each of the pots to make the connection, so you can make this board a little bit more versatile, I guess. We also have some screw mounting holes to here because there wasn't any room because of the routing, and I wanted to keep the board relatively small. There's also two down here at each edge just to give the board a little bit more mechanical rigidity. We'll also notice a ground connection here. That is for a wire that is soldered to the board, which then runs off to a eyelet, which then connects to the metal chassis that the board is sitting on. And down here we've got a pot ground, so you can run a strap over the top of each potentiometer to ground the casing of the pots, so you're not picking up noise when you're touching the shafts of said pots. Now, if we look at the underside of the PCB, because we like bottoms on this channel, you'll notice that these yellow orangey tracks here, these are tinned copper tracks. In other words, they have no solder mask on them, and the idea of that was to increase the amount of current capability of those tracks. Now, these particular power amps in general only draw 355 mA roundabouts into 8 ohms at full power, so there's not that much current going to be flowing through these tracks, but for a design aspect I decided to make these tinned copper rather than solder mask. Yes, it's a lot more work involved putting the zones in to do that. So other than that, there's not much really to talk about this PCB, except our input connector for the AC. We'll notice we've got 24 volt, center tap, and 0 volt. Now, this can be used in several different ways. You can use a single winding transformer between 24 and 0. You could use a 24 volt center tap transformer and just put the center tap connection to one of these pins, because these are two pins that are physically joined but they don't go anywhere else, so you don't have a wire just floating around. Or you could use a 12 volt transformer such as a toroidal. Now, I'd put the current capability of the transformer at 2 amps with both the windings in series with each other, so that's a good starting point. 3 amps is overkill but is suggested. So to run this circuit, I would suggest a 3 amp center tapped transformer at 24 volts total voltage. I wouldn't go any higher than 24 volts. So other than that, there's not much more to talk about this circuit. So now we're going to look at the schematic so we can get a better idea of how this is wired. And you'll notice there's no relay here on the board for muting the output, and I will explain that when we look at the schematic. So here's a look at the redrawn schematic from the magazine, and only the left channel is shown, and all part references, which in this case is like C101, R101, etc. All part references on the right hand channel are 2XX. So if it's R101 here, it's R201 on the right hand channel. The preamp circuitry here hasn't changed much except for the position of the balance control. I've used a traditional balance control with the 1K series resistance, and which I haven't marked, which I probably should, is the clockwise positions of each of these pots. So the clockwise position of this pot goes to the left hand channel, so when the pot is rotated fully clockwise, it actually grounds out the left channel, which would mean that the right channel is the one only outputting any sound, and vice versa. With the base circuitry, I chose a 47 nanofarad capacitor because any lower than that and the base was just way too overpowering when the control was rotated full. And using, say, a 33 nanofarad capacitor, I found that this transistor amplification stage here started to go into distortion really badly, and the power amplifier wasn't really outputting all that much power to start with. So to keep the distortion down, I chose 47 nanofarad. We'll notice a bunch of test points here, test point 1, 2 and 3, and in brackets test point 4. What that is for is to set this sensitivity pot RV101 or RV201. So we inject 250 millivolt RMS into test point 1 or 2, and we measure it on test point 3 or 4 and adjust this till we get 2 volt RMS out. And so that's what those test points are for. Plus it's also handy to, like for test point 3 and 4, to inject a signal directly into the power amplifier for further testing. So speaking of the power amplifier, this hasn't changed much, but I have included voltage measurements around the circuit here, so we've got, places of reference if the thing doesn't work properly. Now we'll notice that the output here, which goes to the speakers, we've got star or asterisk 5.3 volt. Now there's 5.3 volt DC here at the output when it's unloaded. If it's into a load, like 8 ohms for instance, well, that voltage then falls down to 64 millivolts approximately, plus minus, or 8 milliamps. So there's going to be 8 milliamps DC running through the voice coil of the speaker all the time. However, this isn't much of a concern because the speaker should be able to handle it just fine. That's just because of the design of the circuit, and the reason why we have DC here on the output unloaded. You see this 1K resistor here, which I originally assumed was to help discharge this capacitor so that when you connect the speaker load it doesn't produce a pop. Well, it doesn't, and that's because of this 5.3 volt here. We'll notice then it goes off to this other 1K resistor, which on the original schematic at 12 volts should be 680 ohms, and at 17 volts they changed it to 1K. I found at 24 volts 1K is just fine. This is actually a voltage divider between these two resistors, and we're actually now getting the 5.3 volt from the biasing network. So it's coming through this resistor, these two signal diodes, through this resistor to this point, which is then forming a voltage divider with this resistor to ground, producing our 5.3 volts. Now this is the reason why I didn't use a relay, because as soon as you connect the speaker load to this output, that 5.3 volt DC suddenly gets discharged to ground via the voice coil of the speaker, producing clicks and pops. So that means that the relay was pointless. The only reason you would use a relay really is probably to stop the turn-off transients of the power supply discharging, the signal getting lower and lower and distorting, and maybe making a final pop as it turns off. However, this amplifier itself, with the speaker connected all the time, as soon as power is applied, doesn't really produce that much of a thump. It's a very low level pump like that, so it's not really that obnoxious. You could, however, put the muting relay in between the preamp and the power amp's input so that you're getting rid of the turn-off transient of the preamp with the signal fading out and distorting, and any extra turn-on transient or pop that this circuitry may or may not produce into the input of this, causing a louder pop on the output. So looking down at the power supply section, we've got connector input. We've got our full bridge rectifier consisting of 3 amp diodes, 1N5408s, and we get around about 32.9 volt from a 24 volt transformer, DC smooth through the 6800 microfarad 50 volt capacitor, and we've got a ground point here, which is that big wire that goes off to the chassis. We come into this series pass regulator circuitry featuring a Darlington output stage and an error amplifier with a 12 volt reference source using a 1N4742 Zener diode, and that will result in around about 24.6 volts DC at its output, which forms our 24 volt DC rail, which is smooth with this 100 microfarad capacitor and any high frequency noise removed with this 100 nanofarad capacitor. We also have another connector on the board for a 24 volt out, which can be, again, go off to, say, a RIAA phono amplifier, which they do describe in the project pages as well. It then goes through the 78L12 voltage regulator to produce 12 volts here, smooth with this 10 microfarad 16 volt cap with another connector for a 12 volt out, and that can go off to, say, a input selector board for selecting inputs using relays. Over here we have a 1N4004 diode as a half wave rectifier with this 100 microfarad 63 volt capacitor smoothing that, and that was originally to power the relay circuitry, but currently all it does is power an LED to indicate the power is turned on, and so as soon as power is removed, that LED is extinguished immediately and doesn't slowly go out as this capacitor is discharging. This is kind of unnecessary to do it this way, but I didn't really want to remove these two components just in case I want to do another revision and have to add them back to add another muting relay to mute between the preamp and the power amp. That's the whole entire schematic. There's not much else to talk about on it. So the next thing we need to do is look at the physical PCB, and we'll take some measurements after we test it to verify that all these measurements are correct, because the preamps measurements and the power amps measurements were done on a 24 volt DC power supply, not this power supply here, so the voltages may vary. So before this is released as a project, I'm going to make sure, 1, all the voltage measurements are correct, and 2, add the clockwise positions on all the pots so we know which point is clockwise and which is counterclockwise. So alright, let's get looking at the main PCB. Well, a couple of weeks later, the PCBs have materialized. Let's have a look at what we've got, shall we? Oh yeah. Well, we can't see much with the bubble wrap on, so from what I can see so far they look alright. So let's not cut through the moisture absorber, but cut through the other side where it's not. So there we go, there's a good look at the top. Yeah, it came out alright for, well, probably about 6 hours worth of work for routing it. And if we look at the underside, there's all the copper tracks that are exposed with a ground point here, star ground, whatever you want to call it. Yeah, and 4 mounting holes. Excelente. So I'm going to assemble this in time lapse, but I'm going to be doing it without using the assembly tool. I'm going to be doing it on the desk as if someone that doesn't have access to one of those tools would be doing it. And I've written a set of stages of what components to put where, in what order, to make it easy to assemble on the desk. So I'm going to get up the assembly all the way up to the potentiometers, but I'm not going to install them yet, or the ICs along the back side, or this large filter capacitor, or these two 2200 microfarad capacitors, because they're the largest components. They'll get done last. So sit back, enjoy watching me assemble this thing. Okay, and about 2 hours later, most of the construction is done, bar the filter capacitors and output transistors and pots. And there's something very satisfying about this no longer being big and fat. That's what she said. Anyway, that's the bag that the components were in, and it's gotten down a lot less, and that's a satisfying feeling. So now I'm going to turn my attention to the pots, and in my case I've got to cut the shafts down to about 10mm because they're too long. So I'm going to do that first, and then we're going to prep the pots ready for installation, because I'm going to use the provided grounding strap that I've included, so we can stop any noise being picked up by touching the pot shafts. If this was mounted in a fully grounded chassis, metal chassis, then we wouldn't really need to have the grounding strap. But anyway, proceeding on to trimming these down. Alright, the pot shafts have been circumcised. So now I need to roughen the surface, top surface of each pot so I can adhere solder to it. So I'm going to take a round file, and I'm just going to gently mar the surface like that. A little bit more. That should be alright, maybe just a little bit more. There, perfect. I'm going to do the same to the remaining 3, and then we can install them in the board. Alright, now start with the volume pot. There's an awful lot of extra bits of silk screen in places where it shouldn't be, like splash marks. Not sure why. I noticed that when I was assembling it. But yeah, I guess that's just the way it is. Alright, so I'll just solder one center pin so I can get the alignment correct. It's not too bad. Just make sure of that. There we go. That little snap there indicates that it's flush. So solder the other center pin. And yeah, it looks straight. So I can solder the rest. There, pots are in. So the next thing to do is to try and get solder to take to the casing of each pot. So I don't want to heat the pot too much because it will, that was easy, it will cause the pot to lose its smoothness of rotation. It makes it a bit loose, is what I'm trying to say. Take my tin copper wire, and I tin the end where I'm going to start. And try and get it in the center of the pot. There we go. So that's going to go about there. So I need to tin right about here. Missed it. Okay. Yep, I've been doing this over the last few days, and I hope you really appreciate the amount of effort that goes into these videos. Cut it about there. I've just been doing it when I've had time to do it, and it took me about 2 hours to assemble all these components, which is, yeah, maybe considered a little bit of a long time. But so now I can poke that through the pot ground hole, if it will go in the pot ground hole. Oh, it went through. Okay, so I can then use some pliers to pull it through. Bit like that. So now I can solder him to the ground point. Okay. Trim off the excess. And then we should have something that looks like that. As messy as it looks, I mean, it's functional. It doesn't have to be pretty. I mean, once it's inside a case, you're not going to see it. So that's the pots installed. So now I need to turn my attention to the transistors for the output stage and the series pass regulator. So that's going to be my next step. So I'm going to start with the TIP41Cs, and they need to sort of bend so that the metal face of the mounting surface of the transistor extends out towards the edge of the board flush with it, so I can mount to the heatsink. So that needs to be bent at a 45-degree angle and then back on itself again at 45 degrees with probably around about 7 mil to overhang the board. About 7 mil would be about right. Okay, so I'm going to bend it up to where the leg widens. So I can probably do all three at once. Bend it at 45 or thereabouts. And then that's including the body, the distance between the body to the center of the pin to make it 7 mil. So that's going to be I want to say about 5 mil, so about like that. Probably not that sheer of an angle. Something like that. I'll see if that works. I'll put it in the board. Close enough, I guess. Just needs to be straightened a bit. Yeah, that'll work, I guess. Just going to make sure that that is flush enough. I guess when it's bolted to the heatsink, it will pull it straight. So I'm going to do that another 3 times, and then I'm going to mount the series pass transistor. I don't have to bend it as much though. Okay, so I have to be very careful when soldering around near these close traces here, especially this pin here and this outer trace here, because it is awfully close. So we'll have the propensity to short, so I'm going to have to double check that with a multimeter to make sure it's not shorted. But now you can sort of see why I chose to assemble it in a order that I have, because the heights of components make it more easy to work with on the desk. So that's the transistors installed. So now all I have to do is trim the excess leads off. I don't know where that went. So in continuity mode, I'll just check between this pin. It's isolated, so that's good. It should be connected to, well, it's a sealed trace, so that's alright. That one looks okay. This one here. No, it's not shorted. Good. Now to just double check all the transistors are functioning and not damaged. So these are all NPN. I'd say that'd be fine because of how it's in circuit. It seems fine. It's not shorted. That's the same over there, so that's fine. Seems fine. Same over there, that's fine. Good. There's that same 0.032 volt, so that's perfectly fine. Well, there's a touching. Let's try that again. There we go. I can verify that. I'll take my test module and I'll measure between base and emitter. There we go, same voltage. So on the other one, the same. And I know that this module works, so there's no problem. So I guess now it's time to move on to the series pass transistor. So again, I'm going to bend each pin at 45 degrees at the nub of the leg where it gets wider towards the transistor body. And I'm not going to need much of an angle, so I'm just basically eyeballing this. I reckon bending it at another 3 millimeters, so about probably that much, back straight, should be more than enough of an angle sticking out to make the rear of the transistor meet with the heatsink. So something like that. Let's see how well I did. It's almost bloody perfect. That's like spot on. Oh man, I couldn't have got that closer if I tried. Okay, now to try and solder this in. So I'll just tack the center lead in first. That way I can adjust it if I have to. Yeah, that's a bit off. It's probably pretty close. Yep, I'm happy with that. Solder the remaining 2 pins. Again, being careful of this exposed track that's not connected to it next to it. Okay. Just retouch up the middle pin. Trim the excess. Excellent. I'm very happy with that. Once it's bolted to the heatsink, it'll straighten itself out. So again, I'm going to test the transistor to make sure it's still functioning. I mean, it's just a sanity check more than anything else. This base is on the left of this device. That's continuity, not diode. Might help if the multimeter was in frame too. Oops. Good junction there. Excellent junction there. Bit of circuit resistance, but it's not shorted, so collector to emitter, so that's fine. And nothing in that direction. Great. Excellent. Perfectos. And now it's on to the last part of the assembly, and that's the final remaining capacitors, which I left to last. Now, as these are smaller than the filter cap, and I'm going to be using a 4700 microfarad capacitor, 63 volt job snap-in, because I had one lying around because someone sent me 6 of them. I've used the other remaining 5, and this is the one left over. So it's brand new, why not? Doesn't really make that much difference. The higher the capacitance, the better the filtering. But so I'm going to start with the 2200 microfarads because they're smaller and they're going to live where they live, making sure I put them in the correct way round. Right, the output capacitors are installed. Now it's the filter capacitor's turn. Again, installing it the right way around. And that's the biggest component of the board, which is why it was left to last. So here we go. Solder the negative lead first because, well, it's going to take the most heat and time. There we go. And solder the positive. Again, being careful not to bridge between positive and ground here. And that's all soldered in. Nice. And there we go. There's the assembly complete. Now it's ready for testing. So before I begin testing, I've attached a temporary heatsink to the series pass transistor just so it doesn't overheat. And I'm going to use the DC power supply for this because it's easier than a transformer. I don't really have a suitable transformer at the moment. I also don't have the suitable heatsink yet either, but for testing purposes this will be fine. I'll just attach some small heatsinks to these TO220s. Just to prevent them from overheating. So before doing any power up, it's a good idea to check the work to make sure there's no solder splashes, etc. I've already done that. So with the fuses still removed, I'm going to attach my power supply leads directly to the full bridge rectifier because it's convenient. So this will be the positive side. And this one over here, down the bottom, will be the negative side. So, if I can get it on there. And I'll need a multimeter. Set to volts, I'll turn the supply on, and I'm going to set my output current, well, to 200 mA for this test, that's fine. And I'm going to set the voltage to its full maximum, which is 31 volts. And I'm going to turn the load on and look for any unusual current draw. There was a little bit of a spike in current and it's dropped off to about 20 mA now because the filter capacitor was discharged. So if I measure at the bridge rectifier, well, we've got 29 volts coming in because of the drop of the diodes. So that's my negative point there. So if I measure at the 24 volt output, there we go, 24 volts, the regulator is working. And the 12 volts, almost spot on. Excellent, so we've got good voltage. The preamp is connected, so that's drawing current. We're currently drawing 17 mA, that's fine. There's no current being drawn by the power amplifiers. So I can just verify that the voltage is getting to each fuse holder, which it is, and it should not be coming on the other side. No, it is not. We're getting a bit of spurious voltage there because, well, the negative is still connected. So I guess I can turn it off and I will have a look at the discharge rate of the capacitor. It's discharging fairly quickly, actually. That is good. Good. So I want that to discharge to, about a volt before I start doing anything. That's good enough. So before I test the power amplifiers and go to the trouble of mounting a heatsink or some form of heatsink to it, I'm going to set up the preamplifier for its, correct output voltage versus its input voltage. So we want 2 volt RMS going into the power amplifiers with a 250 millivolt rather, RMS voltage going in. So I'm going to set up for that and we'll do that part of the test. I hope it works. Well, it should work. I expect it to work. It should be fine. Let's find out together. First, I'm going to put the volume control full maximum. Make sure the balance control is in the center, and so are the tone controls. Right, let's get set up. Okay, so I've got the oscillator set to 1 kilohertz going into test point 1, which is the left-hand input. And I've got a scope probe measuring the input. The level is set to roughly 250 millivolts. Got the second probe connected to test point 3, which is the left input to the power amp or the left output of the preamp, and we have a problem. Apart from it not triggering, and I'm not sure why it's not triggering. That's a little bit better, we can see it. The output looks like absolute crap. I'm not sure what's going on there. And we've got really no gain either. We've got 525 millivolt coming out RMS. And twiddling the trim pots doesn't make any difference. And the other channel is doing exactly the same thing. So, yeah, that's kind of annoying. So I don't know what is going on there, because if I measure what's coming out of the volume pot, it's a bit distorted, but it's probably because the trim pot is too high. So if I turn the trim pot down, because I was playing with this yesterday, this is the next day by the way, see, we get a reasonably good looking signal. I mean, the bass and treble network are having an effect on the signal, so it looks a little bit lopsided, because if I play with the bass part, see it's changing. So if I go on the input side of that resistor, which is there, it looks worse for whatever reason. I am on the right, there we go, I was on the wrong resistor, that's why. So on the input side of the resistor, after the volume pot directly, the signal looks fine. So I know that the input circuitry of the preamp is working, it's just the output circuitry is not. And I'm wondering why. Golden rule is, when all else fails, thou shalt measure voltages. So I'm really glad before I destroyed the breadboarded version of this preamp that measured the voltages around the circuit and wrote them down, because it's going to help me out a lot right now. So if I ground my negative probe, I want to look at the base of that third transistor in the preamp, which is here. I've got no input signal anymore. So the base is just down here. We've got 0.5 of a volt. Now, it should be 3.8 volt. 0.5 of a volt is not even enough to turn this little transistor on. So this little transistor is not even being turned on. So let me look at the collector voltage now. That should be 9.1 volt. But we're seeing 24 volt. Okay. The emitter should be 3.1 volt. That's over here. Nothing. Bugger all. Which would make sense if the transistor is not being turned on. There's no collector to emitter current flow, and there's no base to emitter current flow either. If I just look at the other channel, the base voltage is exactly the same. The collector voltage is the full 24 volts, which is wrong. And the emitter, bugger all. So there's a clue. So I'm going to need to really study the schematic here and see what I've can come up with. It's not that it's routed incorrectly, it's routed correctly. I checked it 5 times before having it manufactured, so I don't know. I'm going to have to investigate this a little bit further. So here's a look at the output section of the preamp. Here's the transistor in question. So we should have had 3.8 volt on the base, 9.1 volt on the collector, and 3.1 volt on the emitter. Now, I went back and I looked at the original schematic that I redrew this from, and I think I found the problem. There's a 220k resistor here and a 4k7 resistor here directly connected at the base in the center. This is a voltage divider. Now, in the original schematic, this is supposed to be 47k, not 4k7. For some reason, I wrote 4k7. And because I was using this particular schematic, because it was on the desk and handy when routing the PCB, that's the value I put on the silk screen as well. So that could be the reason why it doesn't work. And the reason we're not getting 9.1 volts here, because it's a 4K7 resistor going between collector and the positive rail, is, well, the transistor's not being turned on, there's no collector to emit a current flow, so therefore this resistor is not experiencing a voltage drop. So we will see the full 24 volts here, because there's no voltage drop across that resistor. So that's why that looks weird. So, oopsie, I fucked it up. It's this resistor here for the right channel and this resistor here next to the two 220Ks. Those should be 47K, not 4K7. My bad. Okay, so I'm going to change out those two resistors to 47Ks and test again. Okay, resistors are changed. I just need to find my power supply leads, wherever they've gone. Buried under everything else. And reconnect the power supply. And I'm going to just do those voltage measurements again, and I hope I'm not boring anyone, but this is what happens when you build stuff, that you can tend to make mistakes, as I did. It's all part of the course, unfortunately. So turn the load back on. Okay, now I'll ground the probe, measure at the base now. Ha! 3.8 volts, or thereabouts, moving around. Collector. Now we're seeing 9.9, so it's a little bit higher than I expected, but that's fine. There's now a voltage drop across that 4K7 resistor that goes to the positive rail, as there should. The emitter, 3 volt. Excellent. Second channel, 3.9, a little bit higher than the first one. Yeah. The collector of that one, 9.2, emitter, 3.2. So there's a little bit of difference here and there, but that's just due to circuit tolerances. Alright, let's put the signal back in and back on the scope and see what the result is now. Bloody beautiful. Albeit it is a little bit higher than the required output voltage. It's actually 2.2 volt RMS rather than the 2 volts that is required. So 252 going in, so that's fine. So I'll just trim off that pot like so. Whoops, too far. Bring that up to, if I can. Yeah, it's very fiddly. Around 2 volt RMS. That's close enough. Alright, so now I'm going to swap the input over to test point 2. So that's distorting badly, but that could be because the pot's way too high. So I'll drop him down. Well, that's disappointing. The input on this side is still not functioning correctly. Ah dear. Well, I'm still screwing around and no closer to fixing the issue. Well, it's not actually too bad now. The other channel is a lot more like, you know, not clipping as bad at the top here. But it's got 245 millivolt going in and 1.91 coming out. If I play with the oscillator's, you know, gain and drop it down, the clipping almost goes away. So it just means that the input on that side is just being driven a little harder for whatever reason. It could be due to circuit tolerances or component tolerances. I don't know. I even changed the input transistors. Same difference, and there was no change. But it is working to a point, and the preamp is functioning and is now set up. So yeah, I guess I can move on to testing the power amplifiers. The little bit of clipping there that I'm getting on the output of the preamp is probably not much to be concerned with. I mean, and if anything, I mean, the preamp itself could be probably adjusted down to 1.5 volt RMS instead, just to give it a little bit more headroom at the input. maybe 2 volt RMS was a little bit, you know, generous. So I've been chasing a red herring for the last hour and not getting anywhere. I even checked all the routing again and it is correct. So, I don't know, but it seems to be outputting a signal okay. So next thing to do is to test the power amplifiers. So in order to do that, I need to find some suitable heat sinks to mount to the output transistors so I don't destroy them. So before testing any amplifier, I've got some heat sinks which are all crooked, but it doesn't matter. To test it with, so I'm going to do one channel at a time. Now I've got a ground lead installed so we can measure from ground point at the output, which is over here. So I'll plug one fuse in. I'm going to test the left channel first. So the first thing I want to do is measure what the DC output is. It should be less than 6 volts. So I'm going to apply the power and see if anything goes off with a bang. So here we go. No, seems fine. No magic smoke. So I'll measure between ground and the left output, which is here. About 4.5 volts. Yeah, that's not too bad. Nothing's getting hot. Okay, I can now put that into a dummy load and test its output. Alright, so with the oscillator connected, the volume control set to minimum, I'm going to turn the power back on. A little bit of a jump there, turn the volume up a little bit. And we have an output. Nice. So let me change to square because I want to check the operation of the bass and treble pots, see if they're actually doing what they're supposed to do. That's the treble, full treble, no treble, that seems to be functioning. Full bass, yes. No bass, excellent. At the current volume setting we're drawing around about 270 MA, so that's alright. So I'll go back into sine, and that looks relatively clean. So if I play with the balance pot and put that to the full right hand direction, the left channel goes away. Okay, so we can now do the same for the right hand channel, starting with the voltage measurement and then load it. So let me just get set up for that. Okay, the fuse is now in, so I'll turn the supply back on. The oscillator is disconnected. Nothing went off with a bang, so I'll measure between ground and, if I can get my lead to go on there, ground and the right hand output. About the same as the other channel. Excellent. So these are not isolated, so I've got to be careful with things shorting together. No heat. Alright, I will turn it off and I'll now connect the load to the right hand side, and I'll connect the oscillator to test point 2, which is the right hand input. Now the volume control is still in the same position from the last test, so turn it on. And it's coming up. Look at that. Absolutely bloody beautiful. I'm happy with that, so I'll go back into square and check the operation of the treble again. So that's full treble, that's doing the same thing. No treble, excellent. Full bass, excellent, doing the same as the other channel. No bass, excellent. So if I now rotate the balance pot all the way to the left, the right hand channel goes away as it should. And if I increase the balance a bit, there's a little bit of gain change, but not much. Excellent. The circuit is working, but that is starting to get quite warm to the touch. So I'm going to kill that before I kill it. Because those heat sinks aren't really adequate for this job, but it's okay for testing purposes. So I guess the next thing to do is the most obvious thing to do, and that is a sound test into some speakers. Yee-haw! Okay, it's the next day and I'm ready to test this thing for sound, but first I'm going to turn it on and see if it makes any strange noises. Yeah, a little bit of a pop there. Nothing unusual and nothing that won't hurt the speakers. It's not oscillating. Nothing went off with a bang. Excellent. Next thing I want to know is the turn off transient. Alright, so it farts when you turn it off. But that's fine, I guess. It's not going to hurt the speakers. Alright, now let's play with this thing and hear how it sounds. It sounds pretty good for what it is. Admittedly, I'd already done some sound tests before filming, and I played Year of the Cat through it first because it was a 1976 track, and it kind of goes with the year that this was designed. So that's the first thing that went through it. But yeah, I'm happy with how it turned out. So there will be a link in the description there to the PCB file plus the construction details there as well, if you wish to purchase this, and using this video for some helpful hints along the way of assembly. And we've already found out there's an error on the PCB, so keep that in mind, otherwise it will not function correctly. Other than that, yeah, it's pretty good. So I've even got an LED connected to it. Ooh. Anyway, I'm going to leave this video here. If you enjoyed it, please remember to go down below, comment, like and subscribe if you haven't done so already. And as always, this is the Austereo 30 saying see ya, have an excellent day. Elektor, Austereo.